Hello and welcome back to Calculus 1. No, it's Calculus 3. Hello and welcome back to Calculus 3, section 15.4 on the chain rule. And I should say chain rules because depending on the function and the amount of parameters, you will have different formula for a different setup. What you are used to so far, hopefully, is that z is equal to f of x and y. So let's say z is equal to 3xy minus 4y squared, right? Let's say that's an example of a function. Now this is a multivariable function with two input variables which sit in the domain and one output variable which sits in the range. Now, does this prevent me from having more than these two input variables? No, we're talking about multivariable function. Now, we are fixed on z equals f of xy because it's 1, 2, 3 dimensions. And we like to, right, we live in tridimensional space, three spatial dimensions, so that means that we can measure things and objects. So yes, mainly we would like to have this. However, can we have a 9-dimensional function? Yeah, we can have anything because you can literally write anything. So when you have something like this, you will plug the numbers for x and the y and you will come up with whatever value you get on the other side. We can have more independent variables. We don't have to have just x and a y. We can have a whole bunch of them. Maybe you want to express the temperature as a function of x, y, z, which is a location within the tridimensional object. You see, when you are in this classroom, the air temperature is not equal everywhere because the vents where the cold air is dispensed, right, is going to have that cold air which mixes with other air, gets warmer and warmer as you go away from the vents. It should be hotter near the windows where it's not the sun directly, heat doesn't go through vacuum. I'm not sure if you know that. It's the radiation that hits the atmosphere and then warms up. So sun's radiation warms up the atmosphere and then the warm air outside warms these windows, right? And the glass is going to radiate heat. So you should have a different temperature for the XYZ location around the vent and the different temperature around XYZ, which is around a window location anywhere in there. So we can say that the temperature is some kind of function of XYZ, and XYZ would be a location in 3D. So now you have three input variables controlling capital T, which is another one. So this is the idea of multivariable functions. But now, for a chain rule, we can have each one of these, actually the arrows go other way, each one of these, let's say, be controlled by a parameter time. So, right now, we are in this classroom, school is open, school is in session, air conditioning is on. So you have some kind of temperature at z equals, I don't know, 10, 10, 10, right? Let's say that box is at 10, 10, 10. 10 feet, 10 feet, and 10 feet up. So 10, 10, 10 will have a certain temperature because air conditioning is on and that's where the cold air emerges. But that's happening right now at noon. It's that temperature. Wait 12 hours. The school will be closed. The air conditioning will be off and you will have a different temperature there. So the function at that point is not just dependent on the location, which is XYZ in general, the temperature at the location also depends on the time of the day, because air conditioning might be on or off. Also, during the night, the windows are not going to be as hot as during the day. So there's that, because the planet rotated. It's a ball, right? So it rotates the other way. And when it rotates the other way, the UV radiation from the sun does not heat up the atmosphere around the windows, and it does not make it hot. So what we have here is now the beginning of what we call the nested function, right? What we call the function composition, when you plug in a function to control a function which controls a function. Now, I usually explain that, using the backpack. You think about the backpack when you deal with the function composition, and the backpack has a function. Backpack has only one function: to hold your stuff, right? Now, the content of the backpack is determined by what stuff you put in. Your backpack, you put books in it. Yeah, it's a school bag. You put a parachute in it, completely different, right? If you walk in over here with a backpack that has parachute in it, it's not really helpful. But you definitely don't want to be in a school with a school, right, bag on the airplane as the airplane is going down, right? Parachute is handy. So the content of the backpack determines the use of the backpack, but then there is a function to the stuff that it's in the backpack, and then there is a function of the backpack itself, which is to hold stuff. So the entire function changes as you change stuff that you put in a bag. So you can put a whole bunch of different things inside the bag that will change the purpose of the bag. But the bag is still the bag, right? So when you think about this, you can draw a diagram to break these functions apart. You can say temperature depends on the XYZ location, and each one of these depends on the time of the day that we want to look at this. So this would be a tree diagram of variable dependence. The temperature T depends at the same time, right, at X, Y, and Z, because in three-dimensional system, the location is determined by the three coordinates at the same time. And then when you look at the at each one of these variables, right, independently, they will have maybe some kind of parametric equation that determines their value in time. So if you want a specific temperature, right, the location is going to move, because remember, if you are looking at the you want to find where is, 65 degrees or 70 degrees, whatever. Pick a temperature. With the air conditioning on all the time, that temperature will pretty much be at the same location, which is X, Y, and Z. So let's say this point here is 70 degrees right now. When we shut off the air conditioning, that point is going to move closer, because it can move closer to the vents, because maybe at the vents you have 65, right, temperature. So it's important for us to be able to decompose functions and take a look at the variables that drive that function. And what you find is that you are going to have situation where you have a variable which branches, and then you have the variables that go straight through like this. Those are the different creatures. So if you have a branching, that's going to be partial derivatives. X, Y, or Z, whatever you need. And if you have straight through, it's a regular derivative. So, looking at this diagram here, the derivative of temperature in respect to time going through space is going to be partial of temperature, partial in x, and then you have dx dt. Now you will go, well, why did you use the regular d's over here? Because it's straight through. X depends only on t. And when the variable depends only on one variable, we use the regular calculus 1 derivative. When a variable depends on multiple variables, you use partial derivative. So partial derivatives are when you branch, and then if you have a straight through where the variable depends only on a single variable, you use the regular derivative. So partial derivative of tx plus partial derivative of t in respect to y dy dt. Nice one. Plus partial derivative of t, partial derivative of z, dz dt. So this would be the derivative here. It's like $20 of gas right there. Please note that we added all of the changes together because all of these are pointing towards the time. Now, what I can do also, see, if I am to cancel all of these, dz with dz and dz with dz, you see how you have dt, d plus dt, right? That's a very important aspect of the chain rule. Just like in physics, you're not sure what the formula is, you write something, and if you check dimensions and they work out, most likely you're correct. If the dimensions don't work out, you're definitely wrong, because the left-hand side dimensions of the equation have to match the right side. So if I am calculating change in t, change in temperature in time, well, I better have change in temperature in time in every single one of these when extra stuff is gone. So that's that one. Now, the other one, let's go blue, would be change in z in time, and it's exactly the same thing. Z is the one that branches into x and y, so you have a partial z, partial x, and then you have dx dt, plus partial z, partial y, and then dy dt. So we use a tree to build the formula. Once we have a formula, then we can go and do the rest. So let's take a look at an example of this. Say function w of x, y, and z is equal to 3x squared z minus y squared z plus ln y, whatever. It doesn't matter what you write. But now you have that x is equal to 2t, y is equal to 1 over t, and z is equal to, I don't know, e to the t. It doesn't matter. So usually you are given these, and you are supposed to find the derivative in respect to t. So dw dt is equal to what? You can also use the regular d's here because it's only a t, so it's w and a t. It's, you can use regular derivatives, it's okay. The partial one is when you have two parameters. Let's say you have a parameter t and a parameter s. And that's. So what is the derivative? Well, you draw the diagram, and the diagram will be exactly the same as the diagram that we had for t earlier. W depends on x, y, z, and each one of x, y, z's depends only on t, because the only variable is the variable t, which determines each one of these individually. So we have our formula dw dt as partial w partial x. Why partial? Because w can go into x, y, or z. Because w has choices to go into any of the three. If you need to go into x, you have to use partial. Then you use the regular dx dt because x can only go into t going down the tree. Plus partial w partial y dy dt plus partial w partial z dz dt. This is our formula. Now, once you have the formula, you go and you calculate all of these things. You see partial w partial x. You get that from this equation, right? And then you see derivative of x dt, and it's just going to be 2, looking at this equation here. So what is the dw? What I'm going to do is I'm going to, since I can't fit everything to show at once, I'm just going to copy and then erase this later. So copy, I'll copy it here, so I can see all of the functions as I do calculations. So what is dw dt equal to? Well, partial of w in respect to x. X is a variable, the rest is a constant, so 6xz, sorry, 6xz. The derivative of x squared is 2x, so 6xz. There is no x term here, there is no x term here, so those are all zeros. And that needs to be multiplied by the derivative of x in respect to t, which is just a 2. Plus, now the derivative in respect to y. Well, first term has no y, so that's gone. I have negative 2yz, right, negative 2yz. Plus 1 over y, because that's my derivative of ln y. And I need to multiply this by the derivative of 1 over t, which is negative 1 over t squared. Plus, and now we have dw dz. dw dz, first two terms, the third one has no z. So we have 3x plus 3x minus y squared, because the derivative of z is 1, the derivative of z is 1, and then times the derivative of e to the t in respect to t, it's just itself e to the t. Now observe that you are supposed to provide your derivative in respect to t. That means that you need to replace all of the x and z functions with what they are in terms of t's. If you can simplify anything, simplify and be done. So we are going to now do algebra to simplify this. So 6 times x is 2t, z is e to the t, and then we have times 2, plus negative 2, y is 1 over t, z is e to the t, plus 1 over y is 1 over t is just a t. Everything divided by t squared, and it's a negative in front. Actually, negative can just kill the negative there and change this into a minus. That's good. And then plus 3 times x is 2t minus 1 over t squared times e to the t. There we go. Now I can erase this stuff. Simplify this and we are done. dw dt is equal to 24t e to the t plus, now you have 1 over t over here. If you multiply top and bottom by t to kill that fraction, you are going to have 2e to the t minus t squared divided by t cubed. And then plus, over here you have 6te to the t minus e to the 2t over t squared. Great. So we can combine these terms just to make it nicer. 24 plus 6 is 30 t e to the t. And now we make this one into a t cubed by multiplying by t, so we can combine the two fractions together. So we get plus over t cubed. And what do I have here? I have 2e to the t minus t squared minus te to the 2t. Wow. Cool, huh? It's just a lot of algebra. Let's go back to the problem. This is all it counts here because it's a chain rule section. You have a function w in terms of x, y, z, and then each one of those is driven by a parameter t, let's say time. And w stands for, I don't know, work. So work in certain location in space at certain time t. It changes. So we went through these branches from w to t, and we got every w connected to every t, and we added all of those branches together to come up with a total derivative for everything. You might have more parameters. We talked about parameter arc length as a parameter, which was called lowercase s, and then we used to recast the formula in chapter 13 to use the parameter t. But we can have both of them, right? Because you can parametricize the curve by the arc length, which are these small delta s increments, and then in the object to go from point A to point B uses delta time to go through it. So this is your ds, the arc length, and then dt, the interval in time. So it takes small interval in time to pass small interval in space along this space curve. So we can have a function be driven by two parameters rather than one. And obviously, because it's mathematics, you can have as many as you want, not just two. So what I can have in this case is, let's say I have some function, I can call it whatever, function q of x, y, z, doesn't matter what we put, of x, y, z, and let's say that's going to be some function of x, y, z. And then you have x to be a function of s and t, y to be a function of s and t, and z to be a function, should I use k over there? Yeah, whatever, k, of s and t. So when you draw this diagram, you have a function q on top, and then you have the location for x, y, and z. But now x, y, and z are both, x, y, and z are, all three of those are dependent on two parameters, which is time and arc length. So now this tree branches more. So these variables would impact z and y and then x, and then x, y, z would impact function f, which gives us the final state, right, as you go up the ladder. So in this case, you can either find partial q, partial s, or partial q, partial t. You cannot put these two formulas together in one bag because it's a different independent parameter which drives. So you're either talking in terms of time or you're talking in terms of, let's say, length, right? In terms of how much distance you covered. So all I need is to look at the tree, right? So you look at the equations to draw the tree, and then you just look at the tree to come up with the equations. So in terms of the, let's do parameter t first. And I'm going to actually color code this. So let's go with blue. So you need to find all of the paths from Q to T through the tree. So Q is branching, so partial Q, partial X. And then X is branching, partial X, partial T. Now there is another blue branch, great. I can also get to T from Q if I go through Y. So because there was a branching, it's partial Q, partial Y, and then branching again, so partial Y, partial T. Another one, partial Q, partial Z, partial Z, partial T. Or I can look for partial Q, partial S in terms of the arc length. If I'm looking for that, I should follow the red paths, which would connect Q to S. Partial Q, partial X, partial X, partial S. Partial Q, partial Y, partial S. Partial Q, partial Z, partial S. So I hope you all understand that these equations are not something that you guys memorize. Every time you have a problem, the problem will determine the way in which you write the formula. So when a function depends on 1, 2, 3 variables, you will make it into a tree function that depends on 3 variables. If a function depends on, like x, on 2 variables, then you will make x depend on 2 variables. Now, before, we had x dependent only on a single variable, because as you can see, there was no s or anything like that other than a t, so you have x depending on only 1 variable. Well, w depended on 1, 2, 3 variables, and you can see that w depends on 3 variables. So it's very important to visually be able to quickly create the tree, and once you have the tree, you follow from W to T, from W to T, and W to T. You follow all of the branches that connect W and T, because that's what you are connecting here in a derivative, W to T. Yes, you had to make a stop at X, Y, and Z along the way, but as you can see, those would ever cancel anyway, so you get your dW dt across the board. Say function z depends on x and a y. Awesome. So now your x is going to depend on r, s, and t, 3 different parameters, and your y is going to depend on r and t only. What would the tree look like, and what are the derivatives that you can take? So try and see if you actually got the whole concept of these trees and stuff. Try this. let's take a look at this together. We start with a variable z, and z depends on x and a y, so it will branch into x and a y. Now x depends on 3 variables, so that one will branch, right, 3 parameters. It branches into r, s, and t, and y branches only into r and t. So starting with the z, you can take derivative in respect to r, or s, or t. So we can find, let's say in blue, partial z, partial r. That's going to connect z's to r's in our tree, and we see there are 2 paths, which means there will be 2 terms in our addition. So we go and we say partial z, partial x, partial x, partial r. And there is one more path, which is partial z, partial y, to make a stop, and then partial y into partial r. Let's say there is a purple path that goes through s, and there's only one branch here. So partial z, partial s. And it's just partial z, partial x, partial x, partial s. There is no other s to get to. Single branch, one formula. This is exactly like the one in Calc 1. And then we have the orange path, which is partial z, partial t. That one will have 2 branches, one going through x and one going through y. So partial z, make a stop at x, so partial z, partial x, partial t, plus partial z, now make a stop at y, partial t. When you are given formulas, like we had the example up here, right, you have the functions given to you, you will find partial derivatives and plug where the partial derivatives go. So that was a partial, that was a partial, and that was a partial. And then you will find these extra derivatives. Why is this missing a z over here? There should be a z there. So then you find these extra partial derivatives or derivatives for the t's, and those are the other ones in a formula. Every problem is unique and different as long as you keep changing configuration of how many xyz variables you have, how many parameters. How far does this branching goes? It can go indefinitely, right? We do want to have a finite amount of them, right? You can have 100,000, right? I mean, it's going to take you a lifetime to write the formula, but you can have it. So I can have w to be controlled by variables a and b, and I can have a be controlled by x, y, and then I can have x to be controlled by s and t, and y to be controlled by r and t. And then b to be controlled by x and z, and then you get the idea. So it can get as wild and as crazy as you want. There you go. What are the functions that are involved? Yes?
I had a question about, when you did that last problem, like you had x equals, like, and then you had g in front of it, and then like for y you didn't have anything. Like, what was the difference between?
What do you mean g?
When you showed like you had g and then like r, s, t.
Oh, this?
Yeah. Like,
Oh, I forgot. Yeah. Just I should have an age or something. Yes, function of R. Yeah. Function. It's some function of R and T. So F, G, and H. Yeah, some function. All right. Let's say this crazy tree is given to you. Write the functions. I mean, just you don't know what the functions are, but you know the shape of them, right? So you just say, okay, W as a function of A is a function of A and B. W is a function of A and B. A is some function, and now we use G, F is taken, is some function of X and a Y. B is some function of X and Z. Oh, I have a mistake over here. Look at your X. X is dependent on S and T and then R and S. No. It has to be S and T. There we go. Oops. So now X is going to be some function, I don't know, let's go with K, of S and T parameters. Y is, I don't know, L, function L of R and T parameters. And Z, I don't know, lowercase p, of S, T, and R. So if you have a tree, you can retrieve the functions. If you have functions, you can draw the tree. And you will definitely use the tree to come up with the partial derivatives branching. Now, if you want, let's just do one of these. What's the worst one? T is the worst one because it's in each one of these. So let's say you want, let's go orange, partial W, partial T, right? Partial W, partial T. You have to come up with all of the paths that connect W and T. So you will go W through A through X into a T. W through A through Y into a T. W through B through X into a T. W through B through Z to a T. You have 4 paths that connect W with T. You will have 4 terms in your partial formula. So you go partial W, partial A. That's the first stop you make. Then you have a partial A, partial X, and then finally partial X, partial T. So you had to make these few stops along the way, but you got from W to T. Plus partial W, partial A, and then partial A, partial Y. You're going to the second branch. And then finally partial Y, partial T. So you got to this T going all the way from W up there. Plus, next branch, branch number 3. Partial W, partial B now. Then partial B, partial X, and finally partial X, partial T. We have one more term, partial W, partial B, partial B, partial Z, partial Z, partial T. There they are, 4 terms for 4 branches. There are 4 paths that you can use to go all the way down to T starting at W. You have 3 paths for S, and you have 2 paths for R. So you can also write those at home just to see what the partial W for R and partial. So your problem on the exam for the next test, if you choose to have one, might have a problem which has the, let's say, a tree where you just need to write the formula like this, in which case tree is going to be insane, right? So if you have a problem where you're just writing the formula, most likely tree is going to be insane like this, maybe even bigger, right? And you just have to write something that has, I don't know, 6 terms or something ridiculous, right? Or you are going to have a smaller tree, smaller than this one, with calculations, where you actually have to take derivatives. Now that problem would obviously put together partial derivatives and the chain rule in the same concept, in the same problem for you to practice, and you guys will have that as a problem. Yes?
Why is it that in all the most recent branches, you never did just regular dt or dz or dt?
I didn't have anywhere for a variable to be dependent only on a one variable. They were all branching. If you take a look at any one of these, all of them branch. Only if you have a straight through where a variable depends on one variable, then you have regular d. However, if you put partial for everything for the rest of your life and you completely forget that the regular derivative ever existed, you will never be wrong, because partial derivative is a higher creature. So it assumes underneath right, the derivative from Calc 1. So Calc 3 is this higher power derivative. So if you replace now, you go back and replace every derivative you ever took in your life with a partial, nothing changes, right? The only thing is that you can't use the Calc 1 derivative in terms of the partial one, right? Because the partial one is the right. Remember, you can always do your boss can always do your work. You can't do your boss's work. That's the way it goes. Does that make sense? So straight through. We had.
In the real world, though, you know that's not true. With your
I
parents being able to,
I am yet to find that example. If you have one, please do tell. I am unable to find the example of that. So these will have regular derivatives, as you can see on each one of these, where it only depended on t. But now we have t and s and ts and r and so on, and then they all, because you have to, right? You go to one of the tracks. It's like the train tracks splitting into two. How do I think of it? Then no splits. Use train simulator. All right. Well, that's the chain rule. Bye.